In this chemical kinetics podcast, reaction rates in terms of transition state theory will be introduced, and the role of activation energies in quantifying reaction rates will be discussed. In reality, the energy diagram is a multi-dimensional surface of potential energy of each geometric configuration. The diagram shown is a simple potential surface involving three atoms, and the reaction F plus HCl goes to FH plus Cl. The x and y axes are the FH and HCl distances. The single line diagram, as in the previous slide, is drawn through the minimum of the trough. The transition state represents the state of the reaction at the top of the energy hill. When the molecules have achieved enough energy, the activation energy, they can react. In the transition state, the reactant bonds are starting to break and the new product bonds are starting to form. When the transition state is reached, the molecules can either continue reacting to form products or can break apart again to go back to reactants. The transition state is highly unstable and cannot be isolated. It is different from a reactive intermediate, which does exist for a length of time, even though it is very short. Some surfaces are more complex and impossible to visualize, but if the potential energy line is drawn along the minimum of the trough, from the reactant through the activated complex to the products, some useful information about the complex configurations can be extracted. In trying to determine the product distributions of complex reactions, it is often useful to look at the energies of reactants, intermediates, and transition states. This is an example of the addition of oxygen to a cyclohexane radical. From the diagram, it is possible to justify qualitatively and possibly quantitatively the product distributions. The intermediate molecules in the potential energy minima are the reactive intermediates. But where do the potential energy diagrams come from? An ever-increasingly valuable tool for combustion chemists is to use quantum mechanics. Given a particular structure, quantum mechanics can compute the energy value of the molecule. One of the difficulties is determining the best molecular structures, usually through some optimization process. Another more complicated difficulty is that the transition states are often very complicated electronically. For example, bonds are not quite complete or even stretched. This means that higher order, meaning computationally expensive calculations must be made. In the study where this diagram was taken, the molecular structures and their corresponding potential energies were computed. Another theoretical field that is coming into play in combustion kinetics is that of molecular mechanics. This uses the potential energy surfaces within a statistical mechanics calculation to examine the transition state. Here, for example, the full vibrational behavior of the species, treating atoms as connected with springs, are taken into consideration in determining, for example, rate constants.